Hey folks, it's Mr. Woodward. In this video, we're going to talk about something called elastic potential energy. So let's take a look at the top here. Elastic potential energy is the potential energy of an elastic object that's deformed under tension or compression. So when we say an elastic object, what are we talking about? We're talking about things like springs, bow and arrows, catapults, rubber bands, okay? And this elastic potential energy arises as a consequence of a force that tries to restore the object to its original shape, right? So think about a spring or rubber band. When you stretch it, it wants to go back to its original length. If the stretch is released, then the energy is transformed into kinetic energy. So here I've got a screenshot, of a simulation of a spring. And we're going to take a look at how this works using our friends at PhET and their simulation. Okay, so first of all, this is a spring that I can stretch or compress, okay? And that stretching or compressing is always compared to some sort of equilibrium position, okay? So I'm always going to compare it, if you notice that green dashed line, right, that I'm hiding and showing. As I move the spring compressed away from that equilibrium position or stretched from that equilibrium position, I start to store some potential energy. Okay, down in the bottom left, I have this thing called the spring constant. So if I move this blue slider, you'll notice that the spring gets thicker. If I move the blue slider back the other way, the spring gets thinner. Okay, the spring constant is describing the stiffness of the spring, meaning how difficult it is to stretch or compress that spring. And the spring constant is measured in units of newtons per meter, so it specifically is quantifying how many newtons of force would be required to change the spring's length by a meter. Okay, and then over in the bottom right-hand corner, the displacement, right, is just how much the spring is being stretched compared to its unstretched length. And that displacement can be positive, which would make the spring longer, or the displacement can be negative, which compresses the spring and makes it shorter, okay? All right, I'm going to add some values. So I'm going to add the force and the displacement values. And so now we can see how much force is being applied, how much, that's in orange, how much displacement there is from the equilibrium position, that's in green. And then you can see in the potential energy bar graph at the top, how many joules of potential energy are being stored when you stretch the spring. When you bring it back to its equilibrium position, there's no joules of potential energy. But then when you compress the spring and now push it, make it shorter, then the potential energy goes back up. Okay? So that's generally how a force changes the length of the spring from its unstretched length. And in that process, you actually store potential energy. Okay, now if you're working on a project, like let's say you wanted to measure the spring constant of a rubber band, and specifically how much energy is stored in a rubber band, then you might create a force plot, okay? And the force plot would work like this. On the x-axis, you would measure the amount that you're displacing the object, in this case a rubber band. In the y-axis is the force variable. So as you displace the object and you stretch it, right, that requires more and more force. So this would be a linear graph. As you move up and to the right, more displacement is creating more of a restorative force. The object will want to pull back and go back to its original equilibrium position. And then, by the way, if you've got a graph like this of force versus displacement, it turns out that the area under the graph is the potential energy. So I can check the energy plot. And so what's the area of a triangle? It's always half the base times the height. So if you do the applied force times the displacement and then take half of that, you will exactly measure the potential energy stored by that object that you're stretching. And I gave the example of stretching a rubber band and measuring the force it required to displace it. And therefore, you would calculate the amount of energy that that rubber band could store. Okay, so now that we've looked at the simulation that shows the relationship between the stretch length and the spring constant, meaning the stiffness of the object, and the potential energy, let's take a look at some equations that allow us to calculate some of these things. So the stiffness of an elastic object, such as a spring, can be described by how much force is required to stretch or compress it a certain distance. So we're looking at the force and then the change in length. We will call this stiffness the spring constant. I mentioned this when we were looking at the simulation. And the spring constant, variable K, is always the stretch force or the compression force divided by the change in length of the spring. Therefore, the spring constant is measured in units of newtons per meter. And then down here, if you wanted to measure the energy stored in that elastic object, you would just take half of that K value and then multiply it by the stretch length or the change in length of the object. So let's try that in an example. A spring has a spring constant K of 880 newtons per meter. That means in order to change the length of the spring 1 meter, you would need to pull it or push on it with a force of 880 newtons. So how much must this spring be compressed or stretched to store 45 joules of elastic potential energy? So let's start with our equation, right? Elastic potential energy is equal to half the K value, meaning the stiffness constant, times the change in length squared. We're told that the goal is to store 45 joules of elastic potential energy. We're told that the K value of that spring is 880 newtons per meter of stretch, but we don't know the stretch length. All right, so doing the algebra, multiplying both sides by 2, dividing by 880, we would get that the change in length is delta x squared, which means I still need to take the square root. So that means delta x is actually 0.32 meters, which is 32 centimeters.